Okay, so we are going to continue our study of motion, and now we are going to learn to describe motion graphically. And so for that, we need coordinate systems and we need axes. So typically, we are going to have an x-axis and a y-axis. The x-axis is, by convention, is used for horizontal motion. The y-axis is used for vertical motion, like throwing a ball in the air. So here we have an x-axis, and also by convention, you're always free to choose the origin wherever you want, and by convention, anything right from the origin is positive, and anything to the left is negative. And that is a convention, and you don't have to choose that, and there will be problems where we choose a different convention, but in general that will be what the convention that we'll use in most cases. And same for vertical motion. You're free to choose your origin, and anything above the origin would be positive, anything below the origin will be negative. So a very useful representation of motion is a position versus time graph. Here you have the position, here you have the time. So let's look how to use that for this particular motion here. We have a motion diagram, and so this is your axis here. The axis is an x-axis with the units are in meters. It's 1 frame per minute, so the time from here to here is 1 minute, and from here to here is 1 minute, and the labels are 100, 200, and this is in meters. So you can see there is a constant velocity from this point to this point, then it slows down from this point to this point, and then it goes faster from here all the way to the end. So how do we transfer this motion here, given by this motion diagram, to a position versus time graph? Well, now we will have here in this horizontal axis, which is now a time axis with units of minutes, we'll have the time. So this is 2 minutes, 4 minutes, 6 minutes, 8 minutes, 10 minutes. And on the vertical axis, we'll have the position. This is 200 meters, 400 meters, 600 meters. And now we start transferring the points, right? So the first one is at t equals 0. It is at position 0, that corresponds here. Then the next one is at t equals 1 minute. It is at position 50. That is somewhere over here, so that is this point here. The next one is at position at t equals 1 minute. It is at about 120. That is a little above halfway here, and so on. And then you can see that we have this motion here. So we have this motion here, then here, and then here, like that. So that is your position versus time graph. And we are going to be using this type of graph very often. So once you know that graph, it is easy to obtain the velocity from this type of graph. The velocity is going to be given by the slope of this graph. So remember what the slope is. The slope is just the rise versus the run. So it gives you the inclination here. So that is the slope, and it tells you how fast you're going. So steeper slopes means you're going faster. For instance, here you're going slower, but this one here, you're going faster than this. So this is slow, and this is fast. So once you know how to calculate the speed from the position versus time graph by calculating the rise over the run, then you can start reading and understanding the motion of an object given this type of graph. For instance, here we can calculate the motion from the speed from this point to this point, then the speed from this point to this point, and the speed from this point to this point, simply by measuring at each step the rise over the run, and same here, rise over the run. So now what we can do is make a velocity versus time graph from this position versus time graph. So here we have three segments. We have a segment with this speed, then we have a segment with its speed or velocity, and then we have a segment with its speed. So now we can go ahead and then write the velocity. Here is given meters per second. They transfer the velocity in meters per second, and to do that you have to use this conversion factor that you have to multiply by 60. Basically here it's given to you. So let's see how we transfer this graph here to a velocity versus time graph. So we need to calculate the velocity for this segment. The velocity is going to be constant from this point to about 3 minutes. So that is this here, that is that segment, that is the velocity corresponding to this segment, and that is 1 meter per second. Then here it goes lower, right? You can see that the slope is less inclined than this, so it goes lower. So then we can calculate again the velocity for this segment, and we would get that that is a little under 0.5. That is the velocity for this segment. And finally we have this segment where it is going faster, and so in this segment the velocity is also constant, and we can calculate that velocity there, and that is about 1.6, 1.7. So that is what you can do from a position versus time graph to a velocity versus time graph. Let's do a quick check. We have a motion diagram, and now we want to understand how to transfer this to a velocity versus time graph. So the first thing we need to do then is we need to see what is the position versus time graph. The position versus time graph would be what? Here you have the motion from this point to this point is at a constant speed, so it would be something like this. And then here you have time, here you have position, and then from here to from this point to this point here it moves faster, so you have a steeper slope there. So now using this information, can you figure out which one is the right graph for the right velocity versus time graph for this motion? Take a minute to answer that question. So, and if you do that, then remember that we have this position versus time graph. Here is the time, here's the position, and it was something like this. So here you have some velocity, and then here you have a higher velocity here, and the right answer would be here you have this velocity, which is some value here, and then in the second segment you have a higher velocity there, a velocity with a higher magnitude. So let's look at another graph. This is a position versus time graph for a basketball player moving down on a court. So initially he is here, and then as time passes, this is the position, and then after that he's going to move, the position changes. So what is the right velocity versus time graph? So think about it for a minute, and then we'll come to the answer. So this is the right graph, and let's see what happens. So you can see that as time goes, for this segment, the position is not changing. It is the same. So basically, it is not moving during this segment. So the velocity is 0, right? So it's this time here. Then at this point here, at this time, then he starts moving, and then he starts moving in this direction, right? So this is a negative slope. A negative slope means a negative velocity. So then it would be this one here. So that is the way to understand this position or to obtain this velocity versus time graph from this position versus time graph. So let's look at a final example. You have a car's position graph here. So this is the car, this is the position, this is the time. So then the question is, let's find the velocity versus time graph. And let's just do that one for now. Let's just find the velocity versus time graph. So why don't you try to do this on your own and then come back to the video and see the answer? Okay, if you have tried, then what we need to do is find the velocity in this segment, the velocity in this segment, and the velocity in this segment. To find the velocity in this segment, we need to find the slope. And then the velocity will be delta x divided by delta t. Delta t is what? Is 2 minus 0, that is 2 seconds, right? And delta x is the change. This is your x final, and here is your x initial, right? And that doesn't look like an x. So this is your x initial. So it is final minus initial. So delta x is equal to, the final is minus 4 minus 0. That is equal to minus 4. So then you get this is minus 4. And this is minus 4 divided by 2. And this is meters. And that is equal to minus 2 meters per second. So that is the velocity in this segment here, minus 2 meters per second. In this segment here, the position doesn't change, right? At t equals 0 is at minus 4, and at t equals 4 is at minus 4. So the velocity here is equal to 0. And then finally, for this one here, your x final, for the final segment, your x final is 6. And your x initial is minus 4, so 6 minus 4, that is equal to 10 meters. And then we can calculate then delta x, which is 10 meters, divided by delta t. Delta t is 2 meters, and that is equal to 5 meters per second. So with that calculation now, we can put this into a velocity versus time graph. So the first segment, that is minus 2 meters per second, then 0 meters per second, and then finally 5 meters per second. So that is your, thank you.